Okay, good morning. Now let's try that again. Good morning. Much better. Thank you. It's Friday. We have a long weekend coming up. We should be energized. So, Monday's Labor Day, no class. Okay? I was expecting you guys to be sad for missing my class. Yeah, that's the right reaction. Okay. All right, let's look at Chapter 6, Section 2 today. Last time we talked about areas. Today we're going to talk about volumes. And we're going to use a specific method called the disk/washer method. So many years ago when I taught a similar lesson, one student misread what I wrote and thought I wrote dishwasher method. And so he came up to me after class and said, "What's dishwasher got to do with this stuff?" And I was confused. I was like, dishwasher? But it's not dishwasher. All right, so let's start by looking at the shape. Let's look at the region bounded by y is equal to 2 minus x is equal to 0, and y is equal to 0. Okay, so 2 minus x, we know what that looks like. Straight line with a slope of -1, y-intercept of 2. And it would also have an x-intercept of 2. And then the region bounded by that, x is equal to 0 is the y-axis, and y equal to 0 is the x-axis. So we're talking about this triangular region that's being bounded on all sides by the curves that we put down. So this region here. Now what we're going to do is to revolve this region about the x-axis. You use the x-axis as a pivot, and you take this triangle, and then you rotate it all the way around the x-axis. And picture this in your mind. When you sweep this entire thing once around back to where you started, you will end up getting a cone. Right? Can you visualize that? Yes? Good. What we want to do is to figure out how we can calculate a volume of a shape such as that. Okay, so that's the basic idea here. Let's revisit that triangular region again. And remember, when we calculate the area by using integration, what we're actually doing is to get a bunch of rectangles underneath that. And then we take the limit, allow these rectangles to shrink to almost 0 width, and then let the number of rectangles go to infinity. Notice what happens if I revolve each rectangle around the x-axis. This first one, for example, when I revolve that, I get some kind of disk. right? Can you visualize that? Yes? And then notice this next one here. When I revolve that, I get a slightly smaller disk. And then when I keep going, and so on and so on. So I finally end up something that kind of approximates the cone that we wanted. Now, of course, if I just pile on a bunch of disks like this, I won't get the exact volume. But to get the exact volume, we shrink these to almost zero with zero thickness, and then use an infinite number of disks. So then we shrink the disks. At the same time, use infinitely many. Now, anytime you hear something like that, shrinking and infinitely many, that's an automatic clue that we're doing an integration of some sort. Okay, now let's calculate the volume by adding up these disks. Remember, each disk is dx wide. And we know the disk volume is the area of the circle, pi times the radius squared times the thickness. And you can see from this picture here, when you revolve that, when you get a disk out of it, that means what you started with here must have been the radius of each disk. Does that make sense? The height of the rectangle is the radius of the disk. Okay, so let's see what's going on here. We have our pi radius, which is equivalent to the height of the disk. And what's the height of any disk inside the rectangle, inside the triangle? Top minus bottom, right? Top curve is 2 minus x. The bottom curve is 0. So 2 minus x quantity squared. Thickness is dx. So that's one disk, any arbitrary disk inside that triangular region. And then we have infinitely many of these guys. So we want to sum all of them. We integrate, therefore. When we integrate, we're going to start doing that at x is equal to 0. And we stop accumulating disks at x is equal to 2. Y is equal to 2, sorry. No, x is equal to 2. X is equal to 0, x is equal to 2. And then whenever, at each value of x, we have one of these to sum up. Pi radius squared dx. Okay, so literally that equation is saying we're adding up an infinitely many set of disks, each one having a cross-section area pi times the radius squared, and then a thickness of dx. So the stuff inside here, this is the volume of one disk. And integration says we want to get all of them, starting at 0, ending at 2. Integration is the easy part. Let's take the pi outside. It's a constant. We're allowed to do that. Inside here, something squared. Let's multiply that out. Four, yes. Sorry. Thank you. 2 squared, yeah. Okay, and then pi 4x minus 2x squared plus x cubed over 3, 0 and 2. This is the straightforward part. 8 pi over 3 then. So this is the exact area. It's not an approximation because the act of integration shrinks all of these things into tiny, tiny little slices. So this is the exact same area of that cone that we wanted to find in the first place. Okay, does the basic idea make sense? Where we're slicing disks, find the volume of each disk, and then you integrate over the region. Let's do a few more. Let's get used to the process here. Find the volume of the solid generated by revolving the region bounded by x is equal to radical 3y, x is equal to 0, x is equal to 2, and we're taking that region, revolving that around the y-axis. Okay, we approach it exactly the same way. Start out by sketching the region, and then see how the disks come about. Find the volume of a disk, integrate. Okay, so what shape is this thing here? X is equal to radical 3y. Half a parabola. Which way does it open? To the right. Who else? Upward. Okay, so here's one way you can see. We're used to seeing equation y is equal to blah, right? Let's see what we can do. If I square both sides, then I get x squared is equal to 3y. So that's y is equal to 1/3 x squared. This is a parabola opening upward. The 1/3 changes the width, but the general behavior opening upward doesn't change. And x being the positive radical means it's only 1/2 of it. The positive x half, that means the right half. Okay, make sense? Okay, and then the region bounded by that, x is equal to 0 is right here. Oh, this should be y equal to 2, sorry. So this last curve here is y is equal to 2. I wrote x is equal to 2 earlier. I meant y is equal to 2. So there we go. There's y is equal to 2. The region that's completely bounded by the curves that we specified is this one right here. Almost like a quarter of a circle, but not exactly a circle. It's bounded to the right and below by the parabola, bounded on the left by x is equal to 0, and bounded above by y is equal to 2. And we're taking this to go around the y-axis. Okay, now mentally revolve this around. And what shape do you get out of it? Kind of like a top, right? If you revolve this around here, we get this something like that. Yep. And now here's the key part about the disk method. You set up your rectangle perpendicular to the axis of revolution. That's how you get a disk out of it. One slice of this shape here. So since I'm going around the y-axis, I want my rectangle to be perpendicular to that axis. So I set up the rectangle horizontally like this. See that? It would have a thickness of dy. It's a very small increment in the y direction, so dy. And this becomes the radius of a slice of disk here. Right? Because you can imagine the y-axis coming out of it like that. So that gets spun around and gives you a disk. Once again, the volume of a disk is pi radius squared times the thickness. Okay, so what would the radius here be? Right minus left, right? The outer one minus the inner one. So radical 3y minus 0. Does that make sense to everyone, how we got the thickness? Not the thickness, the radius. And thickness, dy. Okay, when you square this, the radical goes away, so we get 3 pi y dy. And that gives us the volume of one disk, one arbitrary disk inside the shape. We want the whole thing. Now we integrate. We start, because we're integrating in y now, we start at the bottom, 0, and we end at y is equal to 2. 3 pi y dy. That's an easy one to integrate. We get 3 pi over 2 y squared, 0 to 2, and that's a 4 to 6 then, 6 pi. All right, so this thing here has an exact volume of 6 pi, no more and no less. like precisely the volume of that solid right here. Any question with this example? Is this stuff easy, hard, so-so? Okay, let's make it harder then. Okay, it's not that hard, that much harder. It's just one small extension to what we've been doing. No trick today. Okay, in this one here, we're going to take the region bounded by y is equal to x squared, y is equal to x, and we're going to revolve that around the x-axis. Okay, we should know the shape of these two things pretty well. Y is equal to x squared, parabola opening upward. And then y is equal to x, just a straight line with a slope of 1, and the y-intercept is 0. So something like that. So that's the region we're talking about, this half-moon kind of shape. And then we're taking that to go around the x-axis. Okay, now in your mind, we're going to revolve this thing here about the x-axis. So how would you describe what we get out of it? It's kind of like a funnel. Yeah, that's a good description here. The outside wall is, well, from the outside, it looks like a cone, right? Because it's the outside is determined by the straight line here. So the outside looks like a cone. But what about the inside? It's hollow, and it's determined by this rounded shape here. So on the inside, the wall is like that. It's like you take a cone, and then you take a tornado out of it, right? How else would you describe that? But that's what we get. Can you see that? Yep. Okay, let's draw this region a little bit larger here. We're going to work with a rectangle inside. Where do they intersect? This one is pretty easy to see. 1, yeah. If x is equal to 1, y is equal to 1. So that one's pretty easy to see. And we're taking a little rectangle inside that region, going around the x-axis. And now when we revolve this rectangle here, what do we get out of it? It's a washer, yeah. It's not a disk anymore because the center is hollowed out. Think about any slice within this little strange shape here. If you take it out, it'll look like that, right? Like this is a washer. or a donut, or a coin, maybe. Some coins have center hollowed out. Now it looks like a donut. All right, so that little washer is going to look something like this. But what we do is still the same. We find the volume of this washer, and then we integrate over the entire region. How would you calculate the area of that, this little washer here? Very good. So you take the area of the big circle, subtract away the area of the little one inside, and therefore you end up getting this thing, right? So let's see, area of the big one is pi times the outer radius squared, correct? And then subtracting away pi of the inner radius squared. This should be one line, but I'm running out of space there. Does that make sense? And the volume is simply this thing here times the thickness, which we can see from the graph from earlier, which I'll bring it back. Y is equal to x, yeah. And the thickness is a tiny little increment in the x direction, so it's dx. Okay, now we calculate the volume of this washer. First, we calculate the cross-sectional area, pi. Which one is the outer radius? Y is equal to x, the one that's up here, right? That's outlining the outside. That's how we got the cone shape on the outside. So it's x squared. And then the other one that's bounding the inside, that's our inner radius, x squared squared again. So that gives me this area. Then I have a little bit of thickness going into the page in this view, but from here we can see the thickness dx. Okay? So that's one little washer we got. And then we want infinitely many of them. Now we integrate. Your integration bounds always come from the region. That's where we get our slices. So we start slicing at x is equal to 0. And then we stop slicing at x is equal to 1. Yeah, 1. Then we integrate the volume. So that's pi x squared minus pi x squared squared dx. Let's take the pi outside. And then this is x squared minus x to the fourth another easy integration to do, pi x cubed over 3 minus x to the fifth over 5, 0, 1. So 2 over 15 times pi. 2 pi over 15. Okay, does that make sense? Any question? Easy, hard? Yeah, question? Because then what you're saying is you're calculating. That's a good question. Let's talk about that. So your question is why not pi times the outer minus inner squared, right? That's the question you're asking? Okay. So what you're doing here, actually, you're saying that, so suppose this is the outer one. This is the inner one. When you do outer minus inner, so that's our out, and this is our in. Then what you end up getting is something that looks like this. Right? You get a shorter segment here. And when you do pi r squared, you end up calculating a solid disk and not a hollowed out disk. This is just pi times something squared. You end up calculating a smaller disk whose radius is the difference between this and that. But that's not what we want, right? We want a hollowed out washer here. So we have to do the big one minus the small one. That way we get a washer we want. Otherwise it's a disk, and if we pile up disks like this, we get something, but that's not what we want. Okay. Does that make sense to everyone? Good. That's a very good question. Okay, now let's add another layer of complexity to that. We've been revolving around the x and y axes. There's no reason why we can't pick another line to revolve around. And that's what we will be doing next. I'll use exactly the same region to begin with. And this time we'll revolve this around the line y is equal to 1. Okay, the same region we just saw, so let's just get there quickly. And we know this thing will intersect, these two curves intersect at 1, 1. Now this time, last time we revolved around the x-axis. So we're going to revolve around the line y is equal to 1 this time. Okay, and when we revolve this around here, what do we get? Yeah, I like to think of this being the shape of the last one, but turned inside out. If you could actually do that. If you flip it inside out, we get the shape here. So the outside will look like a parabolic kind of bow, but the inside, the wall inside is bounded by the straight lines here. Right? So this axis here, this is y is equal to 1. It's revolved around like that. All right, can you visualize that? Okay, once again, remember, the rectangle you set up is always perpendicular to the axis of revolution. So that means I want to set up my rectangle perpendicular to that. Thickness, again, is dx. All right, now we're going to calculate the outer radius, right? You can see if we do the revolution, we get a washer. So we need to find out the outer radius, the inner radius, calculate the two circles, take the inner one out. Now here's where things get a little bit tricky here. This little red line I drew here, the height of that is x squared, right? And then from the dotted line to the x-axis, it's exactly equal to, not x, 1. And as you can see, the difference between these two is the outer radius. Do you see that? Yep. This black dotted line here, that's the outer radius. Right? When this thing revolves around, that gives us the outline of the outside. So the black line, of course, is the big distance, 1, minus the little red line here, x squared. Any question on how I got that? We're good? Good. Then what would the inner radius be? 1 minus x. Good. Once again, the big thing here, subtracting away the shorter segment here, which is x. From here to here is x. Okay, then the volume of the washer, once you figure these things out, is pretty easy. Pi outer radius squared minus pi inner radius squared, right? Times the thickness dx and that gives you one slice of that shape here. Then we accumulate all of them by doing a definite integration. Zero to 1. Let's take the pi outside right now. Then to integrate that, go ahead and multiply these things out. So this is 1 minus 2x squared plus x to the 4th minus 1 minus 2x plus x squared dx, the whole thing. Right? Okay, what do we get? We get pi 0 to 1, 1 minus 1, so the 1's go away. We have a negative 2x squared minus x squared minus 3x squared. And then we have a positive x to the 4th plus 2x. Let's make sure I did that right. 1 minus 1, that goes away. Minus 2, minus 1 more, so minus 3, positive x to the 4th, minus 2x, so positive 2x. All right. So what do we get? Pi over 5, is that right? All right. Questions about this one? Yeah. No, because the radius has changed somehow. Just because the relative size, the relative width may be different. So not necessarily, even though it's the same kind of thing. But it might have gotten wider or slimmer. Okay, we've got one more example. All right, so this one is a little bit different, but using the same idea we just learned. Let's find the volume of a solid whose base is a circle radius r. Parallel cross sections. Perpendicular to the base are squares. Okay, so this thing is a little bit difficult to visualize. What we got here, let me try to draw that. So there's my circular base. We're looking at this kind of a three-dimensional perspective. So it's a circular round base. But if I were to take a slice of it, each slice will end up being a square. Right? If you look from the bottom, you see a circle, but if you were to slice it this way, you get a square out of it. Don't ask me for a name of this shape. It's whatever it is. And we're trying to find the volume of this. All right, so let's take a look at this thing from the top down. Okay, from the top down here, we see a circle, of course. Radius is r. The equation describing that circle is x squared plus y squared is equal to r squared. What I want to do is to separate this into the upper half and the lower half. So here's the upper half. So you solve for y and take the square root. The positive one goes to the upper half. The negative one goes to the lower half, because y is always negative down here. And up here, y is always positive. So that slice here, looking at from the top down, we just see a rectangle. It again would have a thickness of dx. And how wide is it? How tall is it, I guess? Top minus bottom, so 2 times radical something something. Right? Then the principle is exactly the same. We're not doing any revolution, but we're taking a slice, find the volume of that slice, and then integrate from the left to the right, and then get the entire thing. The volume of each slab, by the way, we know this is a square because the problem said so. Squares. So it's this wide here, also this tall. So therefore, it would be this thing squared. Times dx. Or 4 times r squared minus x squared dx. Finally, the entire thing is going to have a volume of integration from the left, minus r, to the right, positive r. So r here is a number. Treat r as a constant when you integrate. Think of it as a 1 or a 2 or something, but it's a number. And then we integrate this guy, 4 r squared minus x squared dx. Okay? And I'll let you figure out what this turns out to be. And when I upload my notes, I'll have the answer. So work it out yourself and check the notes I upload, and then see if you get it right. All right, that's it. Have a good long weekend. See you Wednesday.